we'll go through the steps for a correlation now. And the first step is identifying the null hypothesis, just like it was for all the previous tests we talked about. And for this example, we're going to work through, we're going to stick with the research hypothesis that exam 1 scores correlate with exam 2 scores. So our null hypothesis is going to be that they're uncorrelated at the population level, rho equals 0. And then the next step will still be to draw the population distribution. And now I'm going to draw it up here, and this is the population distribution. If the null hypothesis is true, and in the past, this has just been a regular distribution of individuals, but now it's going to be a distribution of 2 variables. And so what I'm going to draw is exam 1 and exam 2 scores where they're uncorrelated with each other. So for this, I'm going to draw it a little bit different here than usual. So here's a normal distribution, and that's going to be exam 1 scores. And then what I'm going to try to do is say there's another axis that goes back. Let's see if I can figure out how to draw it. Goes down maybe like so. And we'll say this is our exam 2 scores. And they're also normally distributed. And so this is 2 variables overall relationship with each other here, such that they're uncorrelated. And for this, what I'm going to also do is I'm going to draw this from another point of view. So this is kind of like the side point of view. So I'm going to redraw this, zooming up and looking at it from up top. So we'll have exam 1 on the bottom, exam 2 on top. And now what I'm trying to show is these 2 distributions that are uncorrelated. So for this, since most of the scores are in the middle, I draw a lot of scores in there. And then as you get further out, there's fewer scores. But overall, variable 1 and variable 2 are not related with each other. Right, most of the scores are here in the middle. So I'm trying to draw a population distribution of 2 variables that are uncorrelated, right? And this is a scatter plot. This is the kind of figure that you draw, the kind of graph you draw for correlations. And I wanted to point out that both exam 1 and exam 2 at the population level, we're assuming they're both normally distributed. And actually that for each variable, at every value of the other one, they're also normally distributed. Right, so these are both normally distributed here, and that's called bivariate normal. That just means that the 2 variables are both normally distributed. So it's a bivariate normal population distribution that our correlation is assuming is the case. Next, we'll draw the observed sample distributions. Right, so here we have exam 1 scores and exam 2 scores, and we'll just say they look we'll say that they look like this. These are frequency. And these are our observed sample distributions here. Right, so these are individual scores, and so this might be a particular person's score on exam 1, and that same person maybe got this score on exam 2. Right, so these are the same people that did both exams. And because it's the same people that have 2 scores each, we can actually redraw these distributions as a scatter plot. And we'll say for this particular data that the scores are distributed, something like that. We'll say we calculate the correlation coefficient, and it's 0.64. We're going to skip the calculation of this correlation coefficient for now. I'll come back to it in a little bit. It's a little bit complicated when you have, we'll say we have 100 students in this class. So it's hard to do it when you have a large sample size, so I'm going to show you how to do these calculations with a really small sample size, really small data set. I also want to point out that 0.64 is the actual correlation that I've had in the past in a class in statistics for the exam 1 and the exam 2 scores. So there was a positive correlation for my students in that class. Students who did better on exam 1 also did better on exam 2, and people who did worse on exam 1 did worse on exam 2. All right, and so this is actually the most relevant kind of distribution that we've drawn, right? Because this is what the population looks like if the null hypothesis is true. This is what the sample looks like. So we want to find out, is this the kind of correlation that you expect due to random sampling from this population? And we're hoping to decide this is not the kind of sample you get from this, and we're going to reject the null hypothesis. That's what we're hoping will happen anyways. And just to be clear, this n equals 100, that's 100 students that took exam 1, and those same 100 students took exam 2. So this capital N is all of our students. So there's 100 dots in this scatter plot. So that's what this N equals 100 refers to. So next we will draw the sampling distribution. So that's going to be here. And these are the kind of samples you expect due to random sampling if the null hypothesis is true. And what we're going to do for this is we're going to do a histogram of correlation coefficients. So we'll take a random sample of 100 individuals from this population. We'll calculate their correlation coefficient, say it's 0.6, and we'll put that down here. 0.6 would be right around there. All right, we'll do that for a second sample. We'll say we get negative 0.1. That'd be someplace around here. And we're going to do that for every possible sample of 100. Notice that at the population level, the correlation rho was 0. So that means when we're getting random samples from here, usually we're going to get samples that have a correlation of 0. So that's going to be the most common kind of observed sample that we get. Due to random sampling. But every now and then, right, we could end up getting 100 people that end up having a positive correlation. So every now and then we're going to get positive correlations, and every now and then we're going to get samples with negative correlations. So we're going to end up with a distribution that looks something like this. Right? There's actually a hard cap at 1 and a hard cap at -1 because you can't have correlation coefficients more extreme than either of those. It's going to be symmetrical because by chance you'll get some correlations above 0, some correlations below 0. And just due to random sampling, you don't expect every observed sample to have a correlation of 0. You expect them to vary. In fact, most of them don't actually have a correlation of 0. Usually they're a little bit above or a little bit below. It turns out that the sampling distribution of correlation coefficients is actually a t-distribution. So what we're going to do is we're going to take our correlation coefficients here, and we're going to do a transformation on them. Remember, we did z-score transformations a long time ago. Well, now we're going to transform r scores into t-scores. R statistics, correlation coefficients, into t-statistics. And remember, a t-distribution has a mean of 0, right? And now that we have a familiar t-distribution, what we want to do is put our alpha of 0.05 distributed on the two sides, just like we would do with the t-test. And we want to get our critical values here. So the next step is we've got our critical region and critical values. All right, so our critical values are the t-statistics that have .025 beyond them, so we can look those up in our t-table, and we need our degrees of freedom for that. And for this test, the degrees of freedom is n, capital N, 100, minus 2. And really briefly, where we lost these 2 degrees of freedom, we lost one for calculating the mean for exam 1, and the other for calculating the mean of exam 2. But that might be a little bit more clear in a little bit when I go through how the math works. But for now, just know that the degrees of freedom for a correlation is the number of people that were measured 2 times minus 2. So in this case, our degrees of freedom is 98. So I looked that up on the t-table, and I got the upper critical value to be 1.986 and the bottom to be negative 1.986. And of course, we want to do a two-tail test in case it turns out that even though we expected the scores to be positively correlated, if the scores ended up being negatively correlated, we would have been really interested to know that. And so we want to do a two-tail test, so we'll learn about extreme correlations in either direction, the kind you wouldn't expect from this null hypothesis population. Next, we'll calculate our test statistic. So in this case, we're going to be calculating a t-statistic. So we're going to take the correlation coefficient that we calculated on our raw data, and we're going to convert that, we're going to transform it into a t-statistic. And there's a special formula that you'll need to use to do that. So to get our t-statistic, what we do is we take our observed correlation coefficient, divide that by 1 minus the correlation coefficient squared, divided by the degrees of freedom. And this whole denominator, we'll take the square root of that. So our correlation is 0.64 divided by 1 minus 0.64 squared divided by 100 minus 2 is 98. All the square root. 0.64 1 minus 0.64 squared is going to be 0.59 divided by 98 square root. So when I did this, I ended up with a t-statistic of 8.21. Right, so we can interpret this like we usually do. So a t-statistic is a z-score on the sampling distribution. So the observed correlation is 8 standard deviations over to the right on this distribution. So that's about 2, 4, 6, 8. So our observed sample is right about someplace around here. So this is not the kind of observed sample that you expect due to random sampling from this population up here. The next step is to decide to reject the null hypothesis or fail to reject the null hypothesis. So we'll compare our observed t-statistic with our t-critical values. Our t-statistic is more extreme than our t-critical, so in this case, we will decide to reject the null hypothesis, which means that we are deciding that our observed sample probably did not come from this population. It probably came from a different population. that's not one where there's no correlation between the two variables. Then we interpret the results of our study. So in this case, we decided to reject the null hypothesis. So if we would have failed to reject the null hypothesis, our interpretation would be that our study is inconclusive, but we rejected the null hypothesis. So now we need to figure out, well, is the correlation between exam 1 and exam 2 at the population level a positive correlation or a negative correlation? Well, what we do is we look at our sample and see it's a positive correlation, so our interpretation is going to be that exam 1 score and exam 2 scores are positively correlated. Positive correlation between exam 1 and exam 2. And we can go even further than this. Recall that the correlation coefficient is itself an effect size, the absolute value of the number. Remember, Cohen had the suggestion of .1, .3, and .5 for small, medium, and large effect sizes. Well, we can use this to characterize our finding here. And a large effect size is .5 or so, or bigger, and ours is bigger. So we could say that this is a large effect size.